Hello everyone, in this lecture I will solve the remaining questions of the Fourier series and then we will move towards the half range sine series or cosine series. So let us start with the question. Find the Fourier series of fx equal to x when your x is between 0 to pi, and then this is your 2 pi minus x when your x is between pi to 2 pi. So find the Fourier series of this question and deduce the value of summation 1 upon 2n minus 1 whole square. So here you can see that our interval has the length 2 pi. So we can say that it is a periodic function of period 2 pi. You can also check it with the help of the graph. So as the interval is from 0 to 2 pi, so our Fourier series is fx equal to a0 upon 2 plus summation n equal to 1 to infinity an cos nx plus n equal to 1 to infinity bn sin nx. So this is our Fourier series. Here our a0 will be from 0 to 2 pi, so integral 0 to 2 pi fx dx. You can see that interval, the function fx has two values in two different intervals. So let us break this interval from 0 to pi, and in the interval 0 to pi the fx has the value x, so this will be your x. Then from pi to 2 pi it has value 2 pi minus x. So this is equal to 1 upon pi. Now you can see that integration of x will be your x square by 2, so this will be a pi square by 2, and here the integration of 2 pi minus x will be 2 pi x, and then the integration of x will be x square on 2, then the limits from pi to 2 pi. So our a0 will be 1 by pi square by 2, then the upper limit will be 4 pi square and the lower limit will be pi square by 2. So this is your, here you can see that this is your upper limit, this will be your 4 pi square minus 4 pi whole square divided by 2. So 2 pi whole square, that means minus 4 pi square divided by 2, that means this is your minus 2 pi square. So if x is pi, then this is your again minus 2 pi square. Now this will be your pi square by 2. So these three terms will cancel. Hence pi square upon 2 plus pi square upon 2 means 2 pi square by 2. So a naught will be your pi. So our a naught is pi. And let us compute an. So an will be 1 upon pi 0 to 2 pi fx dx, fx cos nx dx. So this is equal to 1 upon pi. Then again from 0 to pi we have the value of fx as x, so this is your x cos nx, and in the second interval from 2 pi to pi to 2 pi, the value of fx was 2 pi minus x into cos nx dx. So let us integrate this one. Now use the Leibniz rule of integration, the Bernoulli's rule of integration, that means x. Integration of cos x will be sin nx divided by n. Then we have minus sine, the differentiation of x will be 1. Then the integration of sine means cos nx upon n square. And the limits from 0 to pi. Again here the integration of cos nx will be minus sin nx upon n, and then the minus sign, and the differentiation of this one will be minus 1, so this is plus. Again the differentiation of integration of minus sin nx will be cos nx upon n square, and the limits from pi to 2 pi. That's all. So now here you can see that our upper limit and lower limit will be 0 as x is 0, so this will be 0, and at x equal to pi sin n pi is 0. Now this is your minus minus plus, so the first term will be 1 upon pi, this is your 1 upon n square. Now for the upper limit we will have cos n pi, which is your minus 1 power n, and for the lower limit we will have cos 0, which is your 1. Again here you can see that sin 2n pi is 0 and sin n pi is also 0. Again at this point we will have minus 1 power n square, then in the bracket for the upper limit we will have cos 2n pi, which is your 1, and for the lower limit we will have cos n pi, which is your minus 1 power n. So you can see that these two terms are equal to each other, so these two terms can be combined. So this is your 2 upon n square pi, and in the bracket we will have minus 1 to the power n minus 1. So let me check the answer, and this is okay. Now let us compute Bn. Our Bn will be 1 upon pi 0 to 2 pi fx sin nx dx. So this is equal to 1 upon pi. Now as fx has two values, that is x and 2 pi minus x sin nx dx. So let us again use the Bernoulli rule of integration. So this will be your x. Integration of sin x will be your minus cos nx upon n. Then we will have minus sin, and the differentiation of x will be 1. So at this point we will have the difference integration of cos nx, which will be your sin nx upon n square, and the limits from 0 to pi. Again at this point we will have 2 pi minus x, then integration of sin nx will be cos nx upon n, then minus sin, and here the differentiation of 2 pi minus x will be minus, so this is your plus, and again sin nx upon n square, and the limits from pi to 2 pi. Okay, now you can see that sin n pi is 0 and sin 0 is 0, so this term will be 0, and again this term is 0. For this term your upper limit will be 0 as x is 2 pi, and for this term your lower limit is 0, so as x is 0, so its upper limit will exist and this term will have the lower limit. So if x equal to pi, then we will have pi into minus cos n pi, and minus cos n pi is minus 1 to the power n upon n. Again at this point our lower limit will be, now put x equal to pi, so this will be a plus pi, and as we have to put the lower limit, this is your pi into this one, so for the lower limit this will be your minus sign, and then at x equal to pi this will be your pi, and again here we will have minus 1, then cos n pi, that is minus 1 to the power n divided by n. So you can see that these two terms will cancel each other, because here we have plus sign and here we have minus sign, so your Vn is 0. So our Vn is 0. Therefore the Fourier series expansion of fx is equal to a0 by 2, then n equal to 1 to infinity a n cos nx plus bn sin nx. Bn sin nx. So fx was your discontinuous function, and a naught your pi. Now an was 2 upon n square pi. This was your 2 upon n square pi minus 1 to power n minus 1. So this was your an, and bn was 0, so this is 0. Now we have to evaluate the sum of a particular series. Now for that, let us put x equal to 0. Now in the left hand side, our fx was x when your x is between 0 to pi. This was when your x lies between 0 to pi, and this was your 2 pi minus x when your x was between pi and 2 pi. Now at x equal to 0, you can see that the value of function will be at x equal to 0. Here we have the equal to sign. So at x equal to 0, the value of the function will be 0. So your f0 is 0. That means the left hand side is 0. So if the left hand side is 0, then we will have 0 equal to pi by 2. Then from here we will have 2 upon pi. Now as cos 0 is 1, so in the bracket we will have n equal to 1 to infinity minus 1 to power n minus 1 upon n square. So this is your minus pi by 2 equal to 2 upon pi. Now let us put n equal to 1. So if n is 1, then this will be your minus 2 upon 1 square. If n is 2, then this will be your 0. For n equal to 3, again this will be your minus 1, that means minus 2 upon 3 square. Then we will have minus 2 upon 5 square and so on. So this means your pi square divided by 4, and minus 2 will come from this side. So this is your minus pi by 2. Oh, wait for a minute. Here is the product sign. So this will be your, now this minus 2 will come outside. So this minus and minus will be cancelled. So this will be your pi square by 4, and from here we will have 2. So this is your pi square by 8. So the sum of this series is pi square upon 8. So this is the answer. Now let us find out the Fourier series of Fourier series expansion of fx equal to sin x. Let us find out the Fourier series expansion of sin x when your x lies between 0 to pi, and it is 0 when your x is between 2 pi. And further evaluate and reduce the sum of this series 1 into 3 plus 3 into 5 plus 5 into 7 and dot. So first of all, find the Fourier series expansion of this sin x in the interval 0 to 2 pi, and hence evaluate the sum of this series. So again, you can see that the interval is from 0 to 2 pi. So function is periodic of length 2 pi. So Fourier series is fx equal to a0 upon 2 plus n equal to 1 to infinity an cos nx plus n equal to 1 to infinity bn sin nx. Okay, therefore your a0 will be 1 upon pi 0 to 2 pi fx dx. So this is equal to 1 upon pi. Now you can see that function has two values. One is 0 and another is sin x, and value sin x is from sin x, the value of fx is sin x when your x varies from 0 to pi. So we can break this interval in two parts, one from 0 to pi and then from pi to 2 pi. In case of pi to 2 pi, the value of function is 0, so there is no need to write that part. So this will be your 0 to pi fx dx, and in this case the value of the function is sin x. Now the integration of sin x is minus cos x, so this will be minus cos x, and the limits from 0 to pi. As we know that cos pi is minus 1, cos 0 is 1. So this will be a minus 2. So this will be 2 upon pi. So your a naught is 2 upon pi. Now let us compute an. An equal to 1 upon pi 0 to 2 pi fx cos nx dx. So this is your 1 upon pi 0 to, now again the value of the function exists in case of 0 to pi. So in case of 0 to pi, the value of function is sin x cos nx dx. So let us integrate this term. Now we can write it as 2 sin a cos b, and the value of 2 sin a cos b is equal to sin a plus b plus sin a minus b. Now the integration of sin a plus b is equal to minus cos a plus b upon 1 plus n, and again the integration of sin is minus cos 1 minus n, 1 minus n, the limits from 0 to pi. Please note that here n cannot be 1. Please note that as in case of an, our n starts from 1, so here n cannot be 1, so our n will start from 2, so n is 2, 3, 4, 5 and so on. So this is your an. Now let us simplify it. So this is equal to 1.2 pi. Now we know that cos n pi is minus 1 to power n. So here in place of n we have 1 plus n. So this is your minus 1 to power 1 plus n divided by 1 plus n. Again here we will have minus 1 to power n, minus 1 to power 1 minus n divided by 1 minus n. Now for the lower limit, you know that cos 0 is 1, and again for this cos 0 is 1, so we will have plus 1 upon n and plus 1 upon 1 minus n. Now we can break it in two parts, that is minus 1 to power 1 into minus 1 to power n. As we know that minus 1 power n is same as minus 1 to power minus n, so now this minus and minus 1 to power 1 will be plus, and now we will have minus 1 to power n. Again this minus and minus 1 to power n will be plus 1, and we will have minus 1 to power minus n. As minus 1 to power minus n is same as minus 1 to power n, so we can write it as minus 1 to power n, 1 minus n, 1 plus n and 1 minus n. Now we can combine these terms. So take these two terms. So we will have minus 1 to power n plus 1 divided by 1 plus n. Similarly we will have minus 1 to power n plus 1 divided by 1 minus n. So that means this is your 1 plus minus 1 to power n divided by 2 pi. In the bracket we will have 1 plus n plus 1 minus n. So this is your 1 minus n, 1 plus n, that means 2. So this will be your 1 plus minus 1 to power n divided by, in the numerator we will have 2, so this 2 is cancelled. In the denominator we will have pi into 1 minus n square. Again, if n is odd, so if n is odd, then this numerator will be 0 because minus 1 to power 1 will be minus 1. So this is 0 if n is odd, and this will be your 2 upon, we can write it as minus 2 upon pi n square minus 1. So this is when n is even, because if n is odd then this will be a minus 1 plus 1 0. Now if n is even then this will be plus 2, and if we take minus n common from here then we will have minus 2 upon pi n square minus 1. So we have got our an. Now let us compute bn. So bn will be 1 upon pi 0 to pi fx sin nx dx. So this will be your 1 by pi 0 to pi, because we have two values of fx, one from 0 to pi and other from pi to 2 pi. In case of pi to 2 pi, the value of the function was 0. So we are solving it for this case. Please note that here n is not equal to 1. here our n was not equal to 1. Now again we have a formula for sin C sin D, and that will be 1 by 2 sin cos C minus D, that means cos 1 minus x and minus cos 1 plus nx dx. And this is equal to 1.2 pi 0 to pi. As we know that the integration of cos is minus sin, so this will be minus sin 1 minus x, sorry, the integration of cos is plus sin divided by 1 minus n. Again here the integration of cos is sin, and the limits from 0 to pi. Please remember n should not be equal to 1. Okay, now you can see that the upper limit will be 0, because the upper limit means the sin 1 minus n pi. As sin is a multiple of pi, so this will be your 0. Again the low limit will be 0 because sin 0 is 0. So you can see that this term is 0 and again this term is 0. So whole your Bn is 0 for n greater than 2. N greater than equal to 2. Or you can say that for n greater than 1. So now we will have to compute our A1 and B1, because for both our n was greater than 1. So let us compute A1. Now A1 will be, as An was 0 to 1 upon pi, 0 to pi, 0 to 2 pi fx sin fx cos nx. So our A1 will be 1 upon pi, and 0 to, as fx has two values, one from 0 to pi, then other from pi to 2 pi. So we will break it in 0 to pi, and from 0 to pi the value of fx is sin x, and for n equal to 1 this will be your cos x. So again this is your 1 upon 2 pi, this will be your sin 2 theta, so this will be your sin 2x, and the integration of sin 2x will be 1 by 2 minus cos 2x, and this will be your 0, because we know that the cos 2 pi is 0 and cos 0 is 1. Cos 2 pi is 1 and cos 0 is 1, so both upper and lower limit will cancel each other. Now let us compute B1. Similarly, for B1 we will have 0 to pi, the value of fx is sin x. Now in case of Bn we have here sin nx. Now if n is 1, then it will be your sin x. So this will be 1.2 pi 0 to pi sin square x. Now with the help of cos 2 theta, which is your 1 minus 2 sin square theta, so this 2 sin square theta can be written as 1 minus cos 2 theta. So this will be your integral 0 to pi 1 minus cos 2x, and the integration of 1 minus cos 2x will be 1.2 pi, the integration of 1 will be x, integration of cos 2x is sin 2x upon 2. Again sin 2 pi will be 0 and sin 0 is 0, so this will be your pi, and hence B1 is half. Thus our Fourier series, finally Fourier series is fx equal to a0 by 2 plus n equal to 1 to infinity an cos nx plus n equal to 1 to infinity bn sin nx. Now our bn was 0 except when n is 1, so we will start these two series from n equal to 2. So let us take their first term outside. Now in the left hand side we will have the value either sin x or 0. Now a0 was our a0 was 2 upon pi, so this will be your 2 upon pi, that means 1 upon pi. Now our an was, we have already computed our an, and this was your minus 2 upon n square minus 1 pi if your n is even. If n is even, then our an was this one into cos nx, and bn was 0, and again our a1 was 0, so this will be, I am starting with it from the even number, and our bn was 0, but bn is non-zero, so we can write it as b1 sin x, and after this term all the terms are 0 because our bn is 0, and our a1 was 0, so there is no need to write that term. That means the first term of this series, that means a1 cos x, as a1 was 0, so there is no need to write that term, and our b1 was half. So this is the Fourier series expansion of fx. Now further we have to evaluate the sum of the series. So let us put, to evaluate that series, we have to evaluate the value of 1 upon 1 into 3, and then plus 1 upon 3 into 5 plus 1 upon 5 into 7. So for that we will have to remove this term. So let us put x equal to 0 so that this term will get vanished. So because fx was sin x when your x was between 0 to pi, this was the question, yes, and this was 0 from pi to 2 pi. So if x equal to 0, then you can see that the value of the function will be sin 0, and this is your 0. So our left hand side will be 0, and in the right hand side we will have 1 by pi. Now here we have the cos 0 is 1, so this will be minus 2, and equal to even, then n square minus 1 into pi. So this is equal to minus 1 upon pi equal to minus 2 upon pi, and is even when n is even, and in the bracket we have n square minus 1. So in the left hand side we will have half, and in the right hand side, if n is even, that means if n is 2, then this will be a 4 minus 1, that means 3, so it can be written as 1 into 3. If n is 4, then it will be 15, so this is your 3 into 5. If n is 6, then it will be your 35, that means 5 into 7. So your sum of the series is half. In the next lecture, I will give you some examples based on the half range sine series and cosine series. Thank you.